July 1st, 2025, Rio Hurtado, Chile. A telescope catches something moving against the stars. Faint, magnitude 18, fast 130,000 miles per hour. Direction, straight through the heart of our solar system. Within hours, observers worldwide scramble for confirmation. The Zwicky Transient Facility pulls archive images from 2 weeks earlier. The object was already there, already screaming inbound. By July 5th, the orbital mathematics come back with a number nobody wants to believe. Eccentricity, 6.143. Hyperbolic, unbound. This thing didn't start here. It came from somewhere else. Another star, another world. They name it 3I Atlas, the third interstellar visitor we've ever confirmed. The first was Oumuamua in October 2017. Cigar-shaped, tumbling, gone before we could really look. The second was 2I Borisov in August 2019, a proper comet, water and dust, familiar chemistry. But 3I Atlas, different, bigger, older, moving with a velocity that suggests billions of years in the dark. You're holding your phone right now, reading news, scrolling feeds, living your Wednesday. On that same Wednesday, 30 million kilometers from Earth, an object potentially older than our sun is passing through space carrying ice that froze before Earth even existed. Water from another planetary system, dust from a star we'll never see. Chemistry from a time when the Milky Way was young, and we almost missed it. 2 more weeks of delay and the Vera Rubin Observatory would have spotted it first during validation runs from June 21st to July 3rd. But fate put it in front of Atlas in Rio Hurtado, a robotic survey designed to catch asteroids that might hit us. Instead, it caught a messenger from deep time. The Discovery image shows 3I Atlas as a dot in Sagittarius, near the galactic center, dense star fields, easy to miss. Amateur astronomer Sam Dean later found earlier Atlas observations going back to June 5th. The comet was there, moving, active. Nobody saw it because it was passing through the thickest part of the Milky Way's visible disk where 10,000 stars drown out one moving speck. Here's what we know by mid-July. Hubble space. Telescope images from July 21st show a teardrop-shaped cocoon of dust. No proper tail pointing away from the sun, just a forward-facing plume. The nucleus is somewhere between 440 meters and 5.6 kilometers wide. That's a range, a guess, because the nucleus itself is invisible inside the coma. The glow of gas and dust obscures it, but even at the lower estimate, this thing is massive. At the upper end, 33 billion tons, 5 kilometers across, Manhattan Island, end to end. If you value documented astronomy and deep space science like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from the European Space Agency's Mars Orbiter teams. Published October 7th, 2025 at NASA's Jet Propulsion Laboratory orbital databases, updated through October 16th, says the ArcSiv preprint server with spectroscopic analysis by Bin Yang and colleagues from Gemini South Observatory, dated July 20th, 2025. And peer-reviewed astrophysical research from Matthew Hopkins at Oxford, published in July, confirming thick disk galactic origin. These aren't press releases. These are instrument teams and observatories putting their names on data. Now back to the information. Gemini South Observatory in Chile and NASA's Infrared Telescope Facility in Hawaii both aimed spectrographs at 3I Atlas on July 5th and 14th. Bin Yang's team at Instituto de Estudios Astrofísicos ran the analysis. The optical spectrum shows a red slope. 10% per 1,000 angstroms between 0.5 and 0.8 microns. It looks like a D-type asteroid, dark, carbon-rich, organic compounds baked by radiation for eons, but push into near-infrared and the spectrum flattens. 3% per 1,000 angstroms from 0.9 to 1.5 microns. That flattening means water ice. Big grains, 10 microns across. The spectral model fits with 70% Tagish Lake meteorite analog and 30% water ice. That absorption feature near 2.0 microns, water, frozen, ancient, potentially older than Earth. Swift Observatory catches something else on July 31st and August 1st. Hydroxyl radicals, water vapor, not at the nucleus, 4,000 to 10,000 kilometers out. The water ice grains are sublimating in space, not at the surface. Something is pushing them off the nucleus before sunlight can melt them directly. Carbon dioxide, carbon monoxide. Supervolatiles outgassing violently enough to eject ice particles that then turn to vapor far from the comet's core. August 6th, James Webb Space. Telescope turns its near-infrared spectrograph on 3I Atlas. The comet is 3.32 astronomical units from the Sun. Still far out. Cold, but active. The spectra span 0.6 to 5.3 microns. Every wavelength tells a story. Carbon dioxide dominates, not water, carbon dioxide. The mixing ratio is 7.6 to 1, CO2 to H2O, among the highest ever measured. Most comets at this distance show significant water vapor. 3I Atlas barely whispers it. 129 kilograms of CO2 per second, 6.6 kilograms of water per second, 14 kilograms of carbon monoxide, 0.43 kilograms of carbonyl sulfide. The coma is wrapped in carbon dioxide fog. Spherex Space Observatory confirms it on August 8th through 12th. Strong water ice absorption, extended carbon dioxide coma stretching at least 348,000 kilometers. That's almost the distance from Earth to the Moon. A gas cloud bigger than any normal comet produces, and the CO2 keeps pumping. The photodissociation lifetime at 3.2 AU is 4,670,000 seconds. The observed coma size suggests a 700,000 second mean lifetime at 0.48 kilometers per second gas velocity. The math works. This comet is bleeding carbon dioxide at a rate we've never seen. August 21st, Lowell Observatory in Arizona catches cyanide emission. Tentative, faint. August 21st. Again, Very Large Telescope in Chile confirms it. Cyanide and nickel, atomic nickel vapor, nickel without iron. That's unusual. Most comets outgas both. Equal amounts, industrial alloys use nickel without iron. But natural processes can separate them too under extreme radiation or temperature cycling over billions of years. The question hangs, is this chemistry ancient or engineered? Here's where the age comes in. Matthew Hopkins at Oxford and his team traced 3I Atlas backward through the Milky Way. The comet came from Sagittarius, high vertical velocity, 18.5 kilometers per second perpendicular to the galactic plane. That's thick disk motion. The thick disk wraps around the Milky Way's thin disk, older stars, low metallicity, formed when the galaxy was young, stars. There are 7.6 to 14 billion years old, 68% confidence. If 3I Atlas formed around one of those stars, it predates our sun. Our solar system is 4.6 billion years. 3I Atlas could be 14 billion, older than the sun by 9 billion years, older than Earth by 10 billion, a relic from the universe's childhood. Yiyang Guo's team in September traces the comet's path through nearby stars. 25 known stars within 1 parsec in the past 10 million years, none close enough to deflect it significantly. 3I Atlas has been alone, drifting, for millions of years at minimum, potentially billions, mixing with other stars through gravity assists we can't map. Its parent star, unknown, untraceable, gone, maybe, dead, exploded, collapsed, or still burning somewhere in the thick disk, unaware it lost a child eons ago, September 15th to 23rd. Richard Clote, Avi Loeb, and Peter Verez analyzed 4,222 observations from 227 observatories worldwide. They're looking for non-gravitational acceleration, the rocket effect. When a comet outgasses, the jets push it, change its trajectory. 3I Atlas shows no deviation. Residuals in right ascension and declination are consistent with 0. Upper limit on non-gravitational acceleration, 15 meters per day squared. Given the mass loss rate from Webb's data, that means 3I Atlas is heavier than 33 billion tons. Diameter larger than 5 kilometers. Solid density. That's 1,000 times more massive than 2I Borisov. 3 to 5 orders of magnitude heavier than Oumuamua. An anomaly. We should have found 100,000 small interstellar objects before discovering one this big. But we only found 2 before this. The interstellar mass reservoir doesn't support it. There isn't enough rocky material ejected from exoplanetary systems to explain detection rates for objects this size. Either 3I Atlas is a freak statistical outlier, or the models are wrong. Or it's something else. Loeb raises the question: technological origin, rare trajectory alignment with the ecliptic plane, 1 in 500 chance, nickel without iron, no non-gravitational acceleration despite massive outgassing. If it maneuvers, we'll know. Propulsion would show up in the residuals. So far, nothing. Just gravity, just chemistry, just a comet. October 3rd, 2025. 3I Atlas reaches its closest approach to Mars, 29 million kilometers. European space agencies ExoMars Trace Gas Orbiter and Mars Express both turn their instruments toward the comet. NASA's Mars Reconnaissance Orbiter, MAVEN, China's Tianwen-1, UAE's HOPE Orbiter, 7 spacecraft, multiple cameras, spectrometers. The high-rise camera on Mars Reconnaissance Orbiter has a spatial resolution of 30 kilometers per pixel at that distance, 20 times better than Hubble's image from July 21st. The brightest pixel will constrain the nucleus diameter, definitively. No more guessing between 440 meters and 5.6 kilometers. ExoMars. Trace Gas Orbiter's color and stereo surface imaging system captures it first. Released October 7th, 5-second exposures. The comet appears as a fuzzy white dot. Background stars streak because CASes track the comet. The glow extends 680 kilometers. An order of magnitude smaller than the Hubble image, but consistent with surface brightness profiles when you account for the increased sunlight closer to Mars. The primary mirror on CASes is 13.5 centimeters, 300 times smaller than Hubble. It's detecting the brightest region only, missing the faint outer envelope, but it confirms no major outburst happened between July and October. The comet is stable, steady. Outgassing at predicted rates. Mars Express tries with the high-resolution stereo camera. 0.5-second exposures, maximum limit for the spacecraft. Too short. 3, I-Atlas doesn't appear. The spectrometers. Unclear. No public data yet on whether Omega, Spikum, Nomad, or ISEM collected enough photons for spectral analysis, but CASes proves it. The interstellar visitor is real. It's there. It passed through the Martian sky exactly as predicted. NASA's Perseverance rover on the surface tries too. Right navigation camera, NavCam. October 4th at 21:33:39 mean local solar time on Mars. Stacked images over 10 minutes. A streak appears, elongated, 4 times longer than wide. Social media erupts. Cylindrical object, Avi Loeb does the math. 3I Atlas is moving 67 kilometers per second relative to the Sun. Mars is moving 24. Opposite directions. Retrograde orbit, relative velocity produces a path length of 50,000 kilometers over 10 minutes of integration time. The streak is motion blur, not shape. Individual snapshots with 3.28-second exposures would show a circular spot. The composite creates the elongation, not cylindrical, just fast. The high-rise data, not released, not yet. NASA's government shutdown in October delays everything. The website won't update. Images sit in storage, waiting. The brightest pixel in that image will settle the size question. 5 kilometers, 1546. The flux detected by SphereX in August suggests 46 kilometers for 4% albedo. But if 99% of the brightness comes from ice fragments in the coma, the nucleus could be 10 times smaller. 5 kilometers, still enormous, still anomalous, but not absurd. October 29th, perihelion. 3. Bohonai Atlas reaches its closest point to the Sun. 1.36 astronomical units, 203 million kilometers. Between Earth and Mars, sunlight deposits gigawatts of power on the surface. If it's a natural comet, this is when it erupts. Flares, outgassing spikes, maybe fragmentation, breakup, like 2 I Borisov did. Chunks splitting off. Or it holds together. Solid, dense, old. November 2nd through 25th. ESA's JUICE spacecraft observes from its journey to Jupiter. Different vantage point. The comet will be more active post-perihelion. Bright halo, long tail stretching back. JUICE has cameras, spectrometers, particle sensors. Best view of active state. December, JWST observes again. Before and after comparison. Composition changes. Gas ratios shifting as different ices sublimate. Hubble follows with ultraviolet spectroscopy. Gas emissions. Sulfur to oxygen ratio. Monitoring the comet as it leaves. December 19th. Closest approach to Earth. 1.8 astronomical units, 167 million miles. Safe. No threat. Never was. March 16th, 2026. Jupiter flyby. 0.36 AU from Juno spacecraft. 33 million miles. Another set of observations. Another data point. Then outbound. Past Jupiter. Into interstellar space. Escaping the solar system forever. We'll never see it again. But here's what we know now. 3I Atlas is not like other comets. It's carbon dioxide rich, water poor, anomalously massive, potentially 14 billion years old, formed in the Milky Way's thick disk around a star we'll never identify, ejected from a planetary system in the galaxy's youth, drifting alone for billions of years, passing within light years of stars, accelerating, decelerating, mixing through the galaxy's gravitational well until random chance brought it here, to our sun, to our instruments, to our window of observation. The chemistry tells a story. Carbon dioxide dominance suggests formation near the CO, 2 ice line. Colder than Earth's formation zone, warmer than the outer solar system, a sweet spot where carbon dioxide freezes before water, or a surface crust insulating the interior, preventing water sublimation, trapping it below while CO2 escapes through cracks. Either scenario points to planetary system architecture unlike ours. Different snow lines, different volatile distributions, different outcomes. The water ice itself is ancient, 10-micron grains coated in organic tholins, reddish, irradiated. The structure of water ice carries information, crystal lattice, amorphous versus crystalline, impurities, isotopic ratios. JWST detected heavy carbon dioxide, carbon-13. The 12 to 13 ratio is obscured by dust and other gases. Hard to quantify, but it's there. Isotopes from another star's nucleosynthesis, elements cooked in a different stellar furnace. The dust composition resembles D-type asteroids and Tagish Lake meteorite. Dark, primitive, unchanged since formation. But 3I Atlas isn't local. It's not from the Kuiper Belt, not from the Oort cloud. It's foreign, completely alien. A sample from another world delivered by chance. The size anomaly remains. If HiRISE confirms 5 kilometers or larger, the interstellar object population needs rewriting. Detection rates don't support frequent large ejecta. Small bodies like Oumuamua make sense. Tidal forces, planetary scattering, millions of tiny objects thrown into interstellar space by giant planets migrating inward. But 5-kilometer bodies? That requires catastrophic events, stellar close approaches, planetary collisions, ejection of massive protoplanets. Statistically unlikely, yet here it is. The trajectory adds weight. 3I Atlas approached from Sagittarius, near the galactic center. High inclination, 175 degrees, retrograde to planetary motion. It's climbing through the ecliptic plane at a steep angle, 1 in 500 odds. Most interstellar objects would come in flatter, more aligned with galactic rotation. 3I Atlas came from above, or below, tilted. Unusual. Some speculate. Avi Loeb asks the hard questions. Could it maneuver? Could it release probes? Could nickel without iron be industrial? Could the trajectory be aimed? The scientific community pushes back. No radio signals? SETI monitoring detects nothing. No anomalous acceleration beyond measurement error. No deviations from gravitational trajectory. Chemistry fits natural comets. CO2 outgassing explains everything. Occam's razor, simplest explanation, ancient comet. Extreme composition, natural. But the questions linger because the anomalies stack. Age, size, chemistry, trajectory. Nickel without iron. No water tail despite water ice. Forward-facing dust plume. Stable outgassing with no major bursts. Activity at 6.4 AU when most comets stay dormant. Pre-covery observations from TESS show brightness from May 7th when it was 6.4 AU out. Super volatiles driving activity? Not water. Water doesn't sublimate that far from the sun. CO2 does. CO does. This comet woke up early and stayed active through approach. The coma morphology is strange too. Hubble's July 21st image shows elliptical shape, 26,400 by 24,700 kilometers, twice Earth's diameter, slightly elongated. No classic tail, just a teardrop. The dust is moving sunward. Large grains, 100 microns, too heavy for radiation pressure to push back. Internal activity ejects them forward. Small grains, 1 micron, move faster, 22 meters per second. Large grains slower, 2 meters per second. The size distribution and velocity profile indicate explosive outgassing, pockets of CO2 vaporizing violently. Launching material in all directions. Not a steady sublimation, pulsed, episodic. Nickel vapor without iron is documented in other comets, but rare. 2I Borisov showed nickel. Iron 2, equal amounts. 3I Atlas shows nickel. No iron detected. Very Large Telescope spectroscopy from August 21st is clear. Nickel emission lines, no iron lines. Either the iron is there but hidden, or the comet's formation chemistry concentrated nickel preferentially, or space weathering over billions of years altered surface composition. Cosmic rays, solar wind from stars it passed, radiation processing, fractionating elements. The carbon dioxide mystery ties to formation environment. JWST's August 6th spectra show the highest CO2 to water ratio ever measured, 8:1. 6 sigma above the trend for long period comets at that heliocentric distance. C 2016 R. 2 had high CO2 but less extreme. 3I Atlas is off the charts. Formation near the CO, 2 ice line makes sense. Thermodynamic models for protoplanetary disks show regions where carbon dioxide condenses before water. Depends on pressure, temperature, dust-to-gas ratio. If 3I Atlas formed in that narrow zone, it locked in CO2 as its primary ice. Water stayed gaseous, didn't condense, or condensed in small amounts. Alternative explanation: surface crust, low thermal conductivity, dust and refractory material insulate the nucleus. Heat from the sun penetrates slowly, reaches the CO2 ice first, shallow subsurface, vaporizes and escapes. Water, ice buried deeper, stays frozen. Can't sublimate, can't escape. The crust suppresses water release while allowing CO2 to vent. This model explains low water vapor despite water ice grains in the coma. The grains are ejected by CO2 jets, not sublimating at the nucleus. Sublimating later in space. Either way, 3I Atlas formed differently, not like solar system comets. Different star, different disk, different chemistry. We're seeing planetary formation outcomes from another system. Comparative planetology, exoplanetary science, without leaving home. The thick disk origin suggests low metallicity. Parent star had 40% solar abundance of heavy elements, less iron, less silicon, more hydrogen and helium. Older generation star, population 2, enriched by fewer supernovae, formed when the galaxy was metal poor. If the protoplanetary disk around that star had low dust content, planet formation would differ. Fewer terrestrial planets, more gas giants, or no planets at all, just a disk that never coalesced, debris left over, planetesimals that never accreted. 3I Atlas could be a leftover, a failed planet, a chunk that got kicked out before it could grow. Ejection mechanisms vary. Giant planets migrating inward scatter smaller bodies. Stellar close encounters, binary star systems, rogue planets passing through. Each process predicts different size distributions. 3I Atlas, being 5 kilometers or larger, suggests violent ejection, not gentle scattering, collision, disruption, a planetary system that died young. Parent star went supernova? No, too old. 14 billion years is older than most supernovae remnants. Unless it formed before the supernova. Survived the blast? Got kicked out? Unlikely. More likely, planetary migration, hot Jupiters forming at wide orbits, spiraling inward, scattering everything in their path. 3I Atlas caught in the chaos, flung into interstellar space. Galactic dynamics predict close encounters with stars. Guo found 25 stars within 1 parsec over 10 million years. That's recent history. Cosmically speaking, didn't alter trajectory much, but over billions of years, hundreds of encounters, thousands. Each one changes velocity slightly. Speed increases, decreases, direction shifts. 3I Atlas has been pinballing through the galaxy for eons. Its current velocity, 51 kilometers per second away from the galactic center, 18.5 up through the plane, is the sum of all those interactions. We can't trace it back, can't find home. Too many variables, too much time. The discovery rate for interstellar objects is accelerating. Oumuamua, 2I Borisov, 3I Atlas, 3 in 8 years. Vera Rubin Observatory comes online. Full operations. Survey capability increases by orders of magnitude. Predictions say 50 interstellar objects per year, maybe more. Each one a data point, each one a messenger, each one teaching us about worlds we can't visit. The population statistics will answer questions. Size, distribution, composition trends. Are CO2-rich comets common? Or is 3I Atlas unique? Are large bodies rare? Or just hard to see? Do interstellar objects cluster in certain trajectories, or arrive randomly? If you value documented deep space research and verified observational astronomy like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. 3I Atlas will leave the solar system in 2026, outbound past Jupiter. Velocity increasing, escaping, back into the dark. It spent billions of years crossing the galaxy to get here. It will spend billions more crossing to wherever it goes next. If it encounters another star, another planetary system, millions of years from now, will that civilization see it? Will they track it? Will they wonder where it came from? Will they find traces of our observations, radio signals we bounced off it, spectroscopy data encoded in surface chemistry? We'll never know, but we know this. On October 3rd, 2025, Maus, 7 Mars orbiters turned their instruments toward an object from another star. Cameras designed to photograph Mars. Spectrometers built to analyze Martian atmosphere. All retasked, all focused, all capturing light from a comet 14 billion years old. The photons hitting those sensors traveled from ice grains that froze before Earth existed, before the sun formed, before our solar system was a thought. The European Space Agency released the ExoMars Trace Gas Orbiter images on October 7th. Nick Thomas, principal investigator for CASIS, called it very challenging, 10,000 to 100,000 times fainter than Mars. But the instrument delivered fuzzy white dot, 680 kilometers wide, moving against streaked stars. Proof. The interstellar visitor crossed the Martian sky exactly as predicted. No surprises, no deviations, just a comet, just chemistry. Just ancient ice returning to gas as it spirals toward the sun for the first and only time. The high-rise data will come, eventually. When the images release, we'll know. 5 kilometers, 15, 46. The size determines everything. Population models, formation scenarios, detection rates. If it's massive, we rewrite assumptions. If it's modest, we adjust. Either way. 3. I-Atlas is the oldest thing we've ever observed up close. Older than rocks, older than minerals, older than molecular clouds. A frozen chunk of the early Milky Way, delivered by chance, studied by robots, documented by humans. For a few months before it disappears forever. Perihelion happened. October 29th. The comet survived. No fragmentation, no breakup. Steady brightening. Coma expanding. Tail developing. Gemini telescope in Chile captured it, August 27th, with a visible tail, faint, growing. As it rounds the sun and heads back out, that tail will stretch. Millions of kilometers. CO2 streaming behind. Water ice grains sublimating. Dust scattering sunlight. By December now, when Earth observers see it again emerging from behind the sun, it will be different. Brighter. More active. Last chance to look. JUICE observes in November. JWST in December. Hubble monitoring ultraviolet emissions. Parker Solar Probe might catch it, depending on geometry. SOHO coronagraphs, if it passes through the field. Every instrument we have, every spacecraft in position, all coordinated, all gathering data, because this is it. One shot. 3. I-Atlas will never come back. When it leaves, the solar system loses a sample from the thick disk, from the early galaxy, from a star that no longer matters because it's lost in the mix of 100 billion others. But the data stays, spectra archived, images stored, orbital elements calculated to 15 decimal places. Future astronomers will reference it, compare it to 4i, 5i, 6i, build statistics, test models, understand interstellar populations. 3. I-Atlas becomes a benchmark. The oldest, the largest, the most chemically extreme, until something weirder shows up. Matthew Hopkins defended his thesis on interstellar objects 1 week before discovery. He called it fantastic opportunity. Test the model on something brand new, possibly ancient. The Otatahi Oxford model predicted high water mass fraction, observable shortly. They were right. Water ice confirmed July 20th. Activity confirmed even earlier from TESS, pre-covery data, May 7th. The model works. Predictions held. 3. I-Atlas fits. Expectations for thick disk origin? Old star, water-rich formation environment, except for the carbon dioxide. That part's new. That part's teaching us. Chris Lintott at Oxford said it clearly. This is an object from a part of the galaxy we've never seen up close before. 2/3 chance older than the solar system, drifting through interstellar space ever since. Rosemary Dorsey from University of Canterbury in Christchurch said prospects for Rubin are optimistic. We may find 50 objects, some similar in size to 3i. That changes everything. 50 interstellar visitors per year means statistically significant populations, trends, patterns, answers. David Jewett at UCLA, Hubble science team leader, said nobody knows where it came from, like glimpsing a rifle bullet for 1,000th of a second. Can't project back with any accuracy, but we know it came. We know it's here. We know what it's made of: carbon dioxide, water ice, cyanide, nickel, organic tholins, silicate dust, Tagish Lake meteorite analogs, D-type asteroid composition, reddish color from radiation processing, 10-micron ice grains, 100-micron dust particles, all wrapped in a coma twice Earth's diameter. Moving at velocities that prove interstellar origin. The carbon-13 detection in CO2 is crucial. Isotopes record stellar nucleosynthesis. Different stars produce different ratios. Carbon-13 forms in helium-burning shells. Carbon-12 from hydrogen fusion. The ratio depends on stellar mass, metallicity, age. If we can measure 3 I-Atlas's carbon isotopes accurately, we can strain the parent star's properties, even without knowing which star, even without tracing the trajectory back. The isotopes are fingerprints, chemical signatures that identify stellar populations. Thick disk stars have lower carbon-13 than thin disk. If 3I Atlas shows thick disk isotopes, that confirms age, confirms origin, confirms everything. But the dust and gas obscure measurements. JWST saw carbon-13, couldn't quantify abundance, needs better data. Longer exposures, different geometry. December observations might help. Post-perihelion, more active, higher signal to noise, clearer spectral lines. We'll see. Hubble's ultraviolet spectroscopy in November targets sulfur to oxygen ratio. Another tracer, another isotopic signature, sulfur from oxygen-burning stars. Different enrichment history. If 3I Atlas is truly ancient, sulfur to oxygen will differ from solar system values. Might match thick disk abundances, might not. Every measurement constrains models. Every data point narrows possibilities. The trajectory through the solar system is now locked in. Perihelion, October 29th at 1.36 AU. Closest to Earth, December 19th at 1.8 AU. Venus flyby, November 3rd at 0.65 AU. Jupiter, March 16th, 2026 at 0.36 AU. After Jupiter, it's gone. No more planetary encounters, just outbound, hyperbolic escape, 68 kilometers per second at perihelion, speed dropping as it climbs out of the sun's gravity well, but never slow enough to stay, always escaping. The mission proposals came fast. Catch 3, I Atlas, intercept it, send a probe. Comet interceptor launches 2029. We'll wait in parking orbit for a target, pristine comet from the Oort. Cloud? Or interstellar object if one shows up reachable. Michael Kuepers, project scientist, said when Comet Interceptor was selected in 2019, we only knew of one interstellar object, Oumuamua. Since then, 2 more. Large diversity in appearance. Visiting one could provide breakthrough in understanding their nature. But 3I Atlas is moving too fast. Wrong trajectory. Comet Interceptor can't reach it. Future missions. Maybe. If another interstellar visitor comes, if we have years of warning, if the orbit is favorable, 3I Atlas is practice. Proof of concept. We can detect them, track them, characterize them remotely. Next step, touch one. Until then, we watch. Telescopes follow, spacecraft observe. Data accumulates. 3I Atlas becomes the most studied interstellar object in history. More data than Oumuamua, more time than Borisov, better instruments, better coordination, international effort, ESA, NASA, China, UAE, Japan, ground observatories worldwide, amateur astronomers stacking images, professionals running spectroscopy, all contributing, all building the picture. And here's what the picture shows. 3I Atlas is real, natural, ancient, massive, chemically extreme, from the thick disk, 14 billion years old, carrying water ice from another star, carbon dioxide from another disk, cyanide from another chemistry, nickel from another enrichment history, tholins from another radiation field, all compressed into a 5-kilometer nucleus wrapped in a coma twice Earth's diameter, moving at 130,000 miles per hour through our solar system for a few months before disappearing into interstellar space forever. The final data point will come years from now. Some astronomer compiling statistics, counting interstellar objects, plotting size distributions, composition trends, trajectory patterns. 3I Atlas will be 1 point. 1 measurement, 1 confirmed visitor from beyond. But for now, in October 2025, it's everything. It's the mystery, the anomaly, the messenger, the proof that other worlds exist, other stars form planets, other disks make comets, other systems eject debris, and sometimes, rarely, randomly, that debris crosses paths with us. On October 3rd, Mars orbiters photographed it. 680 kilometers of glowing coma against black space, slightly fuzzy white dot moving downward near the center of the frame. Background stars streaking because the camera tracked the comet. Cassis wasn't designed for this. Built to image, Mars hundreds to thousands of kilometers below. Not objects, 30 million kilometers away, but it worked. 5-second exposures, stacked frames, enough photons to register, enough signal to confirm. The surface brightness profile matches Hubble's July image when you account for distance and sunlight intensity. No major change in 3 months. No outburst, no fragmentation event. Just steady outgassing. Predictable. Stable. The comet is holding together. 5 kilometers of ice and rock heated by a sun it's never seen before. heated gradually. Temperature rising degree by degree as it falls sunward. Internal stresses, thermal expansion, cracks forming, vents opening, CO2 escaping, dust lifting, but the structure holds. The nucleus stays intact. That tells us something. Composition, strength, internal structure. If 3I Atlas were loose rubble, barely held together by weak gravity, it would have broken up by now. Tidal stress from the sun, thermal stress from heating, rotational stress from spin. Something would have fractured it, split it into pieces, like Shoemaker-Levy 9 hitting Jupiter, like Comet Ison disintegrating at perihelion. But 3, I Atlas survives. That means it's solid, coherent, maybe a single monolithic block, maybe tightly packed, strong bonds between grains, sintered over billions of years in interstellar space, cold welding, pressure consolidation, whatever process, it made this comet tough. The rotation rate is unknown, no light curve data precise enough, but it's spinning. Has to be. Angular momentum from formation, from ejection, from encounters with stars. Conservation laws demand it. Probably slow. Most comets rotate every hours to days, fast enough to flatten slightly, slow enough to stay together. If 3I Atlas were tumbling fast, irregular shape, we'd see brightness variations. Hubble images would show elongation. Cassius images would show asymmetry. Instead, it's round, symmetric, probably rotating around a single axis, probably close to spherical. That constrains shape, constrains structure. The lack of a proper tail puzzled observers in July. Now we understand. Dust grains too large, radiation pressure can't push them back. They fall forward, toward the sun, creating that teardrop shape, forward-facing plume. By August, Gemini captured a faint tail developing, traditional anti-solar direction. Smaller grains finally getting launched. Water ice grains sublimating far from the nucleus, creating vapor, creating hydroxyl, creating the classic comet appearance. But it took time, took heating, took approach to 3 AU and closer. At 6.4 AU in May, the comet was already active. Tess observed it, brightness beyond what bare nucleus could produce. That's super volatile activity, CO, CO2, methane maybe, nitrogen compounds, things that vaporize at extremely low temperatures, things that don't wait for the sun to get close. 3. I Atlas woke up early because its chemistry allowed it. Most comets stay dormant outside 4 AU. 3 I Atlas doesn't follow the rules because it's not from here. Different ices, different equilibrium temperatures, different sublimation curves, the dust-to-gas ratio matters. Observations suggest high dust content, lots of particles, lots of scattering. That's why the coma looks bright despite faint gas emissions. The dust reflects sunlight efficiently, micron-sized grains, optimal size for visible wavelengths, scattering cross-section peaks. Makes the comet appear larger than it is, makes it detectable from Earth at magnitude 16 to 17 when the nucleus itself would be invisible. The reddish color comes from tholins, organic macromolecules made from methane, nitrogen, carbon compounds exposed to radiation. Cosmic rays over billions of years, ultraviolet from stars, charged particles from the interstellar medium. Each impact breaks bonds, creates radicals. Radicals recombine into complex chains, polymers, long-chain hydrocarbons, nitriles, polycyclic aromatics. All this chemistry happening in interstellar space while 3 I Atlas drifted. The surface got redder, darker, more organic rich, protecting the interior, insulating the pristine ice below. That's why the coma material looks different from surface spectroscopy. The coma samples subsurface ice, fresh material, ejected by outgassing, not radiated, not processed, still carrying primordial composition, while the nucleus surface shows billions of years of weathering, space radiation, micrometeorite impacts, cosmic ray spallation. The surface is a radiation shield, the coma is a time capsule. When JWST observes in December, it will see post-perihelion chemistry, different ices sublimating, water finally vaporizing in significant amounts, thermal penetration reaching deeper layers, releasing compounds locked below. Ammonia, methanol, formaldehyde, hydrogen cyanide beyond what VLT detected, complex organics. Each compound tells part of the formation story. Each ratio constrains disk temperature, pressure, composition. The December Earth apparition will be the last good look. After that, 3. I Atlas recedes, gets fainter, moves into regions only large telescopes can reach. By February 2026, magnitude 20. By March, past Jupiter, effectively invisible except to Juno. After March, it's gone from human view. not gone from existence, still there. Still moving, still carrying its ancient ice and pristine chemistry, just too far, too faint, too fast. The trajectory leads out of the ecliptic, back above the galactic plane, returning to thick disk orbits. It will pass other stars, eventually, millions of years from now. Will it encounter another planetary system? Statistics say maybe 1 in thousands, 1 in millions. Depends on stellar density where it goes. Depends on speed. Depends on random chance. Same chance that brought it here. If it does encounter another system, what will they see? A comet. Ancient, scarred by interstellar travel, cratered by impacts, eroded by radiation, but still intact, still carrying ice. If they have detectors, spectrometers, they'll measure composition. They'll find carbon dioxide, water, cyanide, nickel, tholins. They'll wonder where it came from. They'll trace trajectories back. They'll hit the same wall we do. Too many variables, too much time, can't find home, but maybe they'll find something we left, not intentionally, not a message, just consequences. Radio reflections, radar pings, photons we scattered doing spectroscopy, laser ranging if anyone tried, charged particles from solar wind we diverted, tiny effects, probably undetectable, but theoretically there, imprinted on the comet's surface and coma during its passage through our system, evidence that something observed it, something intelligent, something curious. We'll never know if they find it. We'll never know if the Atlas encounters anyone. We'll never hear back. It's a one-way observation. We see it, study it, document it. It leaves, end of story. Except for the data, except for what we learned, except for how it changed our understanding. Before 3I Atlas, we thought interstellar objects would be small. Oumuamua was 100 meters. 2I Borisov 500 meters. 3I Atlas is 5 kilometers minimum, maybe 15. Orders of magnitude larger. That changes population estimates, changes formation models, changes ejection mechanisms. You don't toss 5-kilometer bodies into interstellar space easily. Requires violence, energy, catastrophic events, not gentle scattering by planets. Something more. Before 3I Atlas, we thought interstellar comets would resemble solar system comets, water-rich, similar chemistry. 2I Borisov fit that pattern. Normal comet, normal ratios. 3I Atlas doesn't. Carbon dioxide dominates. 8-to-1 over water. Never seen. That means planetary systems form differently. Disk chemistry varies. Ice lines shift. What freezes, where, depends on stellar mass, luminosity, disk density, dust-to-gas ratio. 3I Atlas formed in conditions we don't have locally. Teaches us about exoplanet systems we can't visit. Before 3I Atlas, we thought we knew detection rates. Statistical models predicted we'd find many small objects before finding large ones. We found 2 small ones, then 1 huge one. Either we're incredibly lucky, or the models are wrong. Or 3. I Atlas represents a different population. Maybe thick disk ejecta are larger. Maybe old planetary systems produce bigger comets. Maybe ejection efficiency scales with size in ways we don't understand. The data doesn't fit predictions. That's exciting. That means discovery. The Mars observations matter because they're the highest resolution we'll get. 30 kilometers per pixel on HiRISE, 30 times better than Hubble. The brightness of that pixel constrains surface area. Surface area gives diameter. Diameter gives volume. Volume times density gives mass. Mass determines everything. If mass is 33 billion tons, diameter is 5 kilometers. That's solid density. 2 grams per cubic centimeter. Rock and ice. Compact. Coherent. If mass is lower, diameter is smaller, density is higher. 3 grams per cubic centimeter. 4. That would be unusual. Would suggest metal content. Wouldn't fit carbonaceous composition. But if mass is higher, diameter is larger, 10 to 15 kilometers. Density drops 1 gram per cubic centimeter. 0.5. Porous. Fluffy, rubble pile barely held together. Each scenario tells a different story. HiRISE will decide. When NASA releases the data, when the government shutdown ends, when the images get processed, weeks, months. Eventually, the scientific community waits. Avi Loeb writes medium posts daily, analyzing, speculating, calculating. He wants that image, needs that pixel brightness, has predictions to test. If nucleus is larger than 5 kilometers, he argues, natural origin becomes untenable. Interstellar mass reservoir can't support it. Alternative explanations required. Technological origin, artificial object. Spacecraft, probe. Most scientists disagree. Point to SETI observations. No radio signals, no anomalous emissions, no deviations from gravity-only trajectory. chemistry fits natural processes. Go 2, outgassing explains everything. Nickel without iron is unusual but not unprecedented. Cyanide is normal for comets. Water ice is expected. Tholins are everywhere. Nothing technological, nothing artificial. Just an old comet with extreme composition from a different formation environment. The debate continues because the anomalies persist. Rare trajectory. 1 in 500 chance of ecliptic alignment. Large size, 3 orders of magnitude above previous interstellar objects. Extreme chemistry, highest CO2 ratio ever. Stable structure, no fragmentation despite thermal stress. Early activity, already outgassing at 6.4 AU. Nickel without iron. Unexplained unless natural fractionation or selective outgassing. Each anomaly has explanations. Natural explanations. But altogether, statistically unlikely. Not impossible, just unlikely. Science demands evidence. Extraordinary claims require extraordinary proof. Loeb has questions, valid questions, but questions aren't answers. Data decides. High-rise data, JWST data, Hubble data, JUICE data, accumulated observations over months. When the campaign finishes, when all instruments have looked, when all spectra are analyzed, the picture will be complete. Then we judge, then we decide, natural or artificial, ancient comet or technological artifact. My money's on natural, comet, ice and rock, old, massive, chemically unusual, but natural. Formed in a protoplanetary disk around a thick disk star 7 to 14 billion years ago, ejected by planetary migration or stellar encounter, drifted billions of years through the galaxy, passed 25 stars in the last 10 million years, approached our solar system by chance, got heated by our sun, released gases, developed coma, survived perihelion, left the system forever. Simple story. Requires no new physics, no alien technology, no conspiratorial thinking, just chemistry and gravity and time. But I could be wrong. High-rise might show something unexpected. Geometrically perfect shape, artificial reflectivity, surface features inconsistent with natural processes. JWST might detect isotopes that don't fit stellar nucleosynthesis, abundances impossible from natural disk chemistry. Hubble might catch anomalous emissions, spectral lines from industrial compounds, alloys, refined materials. If that happens, we rewrite everything. For now, we wait. The comet swings around the sun, gets brightest, gets closest, gets most active. Instruments watch, data flows, archives fill, papers get written. Preprints submitted. Peer review begins. The scientific process grinds forward. Slow, careful, methodical. No jumping to conclusions, no premature announcements, just data, just analysis, just incremental progress toward understanding. December brings the last observations from Earth. Then 3, I-Atlas dips below detection limits, fades into deep space, becomes a catalog entry. Object 3I, third interstellar visitor, discovered July 1st, 2025, perihelion, October 29th. Closest approach to Earth, December 19th, diameter uncertain. Composition, carbon dioxide rich with water ice, cyanide, nickel. Origin, thick disk, age 7 to 14 billion years. Exit trajectory above galactic plane. Hyperbolic excess velocity, 58 kilometers per second. That catalog entry will sit in databases forever. Future astronomers will reference it, compare new interstellar objects against it, build statistical populations, test formation theories. 3, I-Atlas becomes the baseline, the template, the prototype for carbon dioxide. Rich interstellar comets from ancient stellar populations. If we find more like it, we learn it's a class, a category. If we don't, it's unique, one of a kind. Either way, it matters. The discovery images from Atlas in Chile on July 1st will be historic. First light on 3 Alpiconard. First photons captured. Those images show a faint dot. Magnitude 18, moving 1 arc second per hour. Nothing special visually, but in hindsight, everything. That dot was 14 billion years old. That dot came from another star. That dot carried water ice from the early Milky Way. And a robotic telescope caught it, flagged it, reported it, started the campaign that brought dozens of instruments, hundreds of astronomers, multiple space agencies together to study it. Thank the engineers who built Atlas. Thank the software that detected motion. Thank the surveyors who programmed the search patterns. Thank the Minor Planet Center for Coordination. Thank every amateur astronomer who contributed observations. Thank every professional who aimed a telescope. Thank ESA for Mars orbiters. Thank NASA for Hubble and Webb and Perseverance. Thank everyone who made this possible. 3. I-Atlas didn't care. Doesn't care. It's a comet. unconscious, indifferent, following physics, but we care. We noticed, we watched, we documented, we learned. That's what makes us different. That's what makes us human. Curiosity, the drive to understand, the need to know where things come from and where they're going. October 3rd, 2025 will be remembered, the day Mars orbiters photographed an interstellar visitor, the day ExoMars Trace gas orbiter captured that fuzzy white dot, the day we got the closest look at ancient ice from another star, not the closest we'll ever get. Someday we'll send a probe, intercept an interstellar object, land on it, sample it, bring pieces back, analyze in laboratories, measure isotopes precisely, determine exact composition, confirm theories, answer questions, but that's future, decades away, maybe centuries. For now, we have remote sensing, spectroscopy, photometry, astrometry, indirect measurements, inferences, models fitted to data, best guesses based on physics and chemistry and observations. It's enough. It's more than enough, because 20 years ago we had nothing. 0 interstellar objects, 0 data, just theories, predictions, statistical arguments that they should exist. Now we have 3. Soon, more. The population is revealing itself. The galaxy is sharing its secrets. 3. IATLAS taught us planetary systems eject material, lots of it, large pieces, comets kilometers across. They drift between stars for billions of years. They survive. They stay cold. They preserve primordial ice. When they pass through solar systems, they heat up, release gases, become detectable. We can study them, learn about distant worlds without traveling there. Comparative planetology across light years, understanding star formation across billions of years. Time-resolved chemistry from the early galaxy to now. The water ice in 3 IATLAS is pristine, 14 billion years old, never melted, never boiled, never contaminated by biological processes, just pure water. H2O molecules frozen in crystal lattice. Locked in place since formation, carrying deuterium to hydrogen ratio from the parent cloud, oxygen isotope abundances from the star's nucleosynthesis, chemical memory, a record of conditions that no longer exist. The stellar neighborhood where 3 IATLAS formed is gone, changed. Stars moved, died. New stars formed, nebulae dispersed. The galaxy evolved, but this ice remembers, holds the information, delivers it to us. When water vapor sublimates from 3 IATLAS coma, those molecules scatter sunlight. They absorb ultraviolet. They fluoresce. They create hydroxyl radicals. Each process is detectable. Each process reveals isotopes. Deuterium in water shows up in UV spectra. Oxygen 18 versus oxygen 16 shows up in infrared. Carbon 13 in CO. 2 shows up in JWST data. All these isotopes constrain formation, disk temperature, stellar metallicity, enrichment history. We measure ratios, compare to solar system values, compare to other interstellar objects, build patterns, understand trends. If 3 IATLAS deuterium to hydrogen ratio is higher than solar, that means it formed farther from its star, colder regions, where deuterium enrichment in water ice is higher. If ratio is lower, it formed closer in warmer regions, depleted deuterium. If ratio matches solar, it formed in similar conditions. Same temperature, same disk chemistry. We don't know yet. Need better spectra. December observations might provide it. Hubble UV spectroscopy targeting hydroxyl emission, looking for deuterated water, OD versus OH. Ratio gives answer. Oxygen isotopes are harder, require high-resolution infrared spectroscopy. JWST can do it. If signal to noise is sufficient, if spectral lines are resolved, if atmospheric contamination is minimal, big ifs, but possible, worth trying. Oxygen 18 enrichment indicates neutron-rich nucleosynthesis, massive stars, supernovae enrichment. If 3 IATLAS parent star was low metallicity, formed from pristine gas with minimal supernova enrichment, oxygen 18 will be depleted. If parent star formed later, after many supernovae, oxygen 18 will match or exceed solar. Test of stellar population. Confirmation of thick disk origin. The science is elegant. Isotopes as clocks and thermometers and tracers, measuring them remotely across billions of kilometers, inferring formation conditions billions of years ago, around a star we'll never identify, in a disk that dispersed ages ago, creating knowledge from photons, building understanding from spectral lines. This is what astronomy does, extracting cosmic history from light. 3 IATLAS is